Hello, ladies and gentlemen. My name is Luis Moya. I'm from the Japan Peru Center for Earthquake Engineering Research and Disaster Mitigation from the National University of Engineering in Peru. So today I want to show you my work regarding the automatic algorithms to detect affected buildings after a large-scale disaster. So this is what basically we use. We actually have two images recorded before and after a disaster, and my job is to identify which buildings were highly affected for that disaster. Okay, and here I'm just showing an example of my job. So on the left side we have the radar images that we use to identify affected buildings due to the tsunami in the 2018 tsunami earthquake in Indonesia. So on the right side, you can see our results. That you see the white pixels denote the urban non-affected buildings, and on the purple pixels, you see the affected infrastructure, affected buildings. So what we actually use is machine learning algorithms to identify those buildings. And as you may know, machine learning techniques requires training data, and this is one of the main issues in this kind of job. In this main target is the availability of training data. I think you agree with me that the best source of information regarding samples is by performing field survey of the affected area, but it is almost impossible because it's highly risky to go there and collect data, right? So maybe it's not possible for early disaster response. Another option is to perform a visual inspection of some areas using high resolution optical images, but this option has also some shortcomings. So what I'm showing here is an example of the mistake that was performed by this team, that they labeled some buildings as collapsed due to the tsunami, but actually it was demolished by human because they were reconstructing old buildings. Another option, and I think is the most used currently, is to gather information, training data from previous disasters, and gather a very big database and calibrate the algorithms to use for a current event. So this is an example. I'm sorry, this is an example of a typhoon, but I just wanted to convey the idea. There is an example in which we use information from the 2018 heavy rainfall and apply to identify flooded areas due to the Hagibis typhoon that get into the area of Japan in 2019. Okay, so this option, which is quite popular now, has also some problems. And this is one example. The European Space Agency recently published that they will have in future a new satellite image for radar images with L band. This is a different band that they have comparing with the one they have now. So it means that if we want to use this new data that it will be in future, we have to collect again. We have to start over the collection of disasters. So I just want to emphasize that collecting data from previous event has also some problems. Okay, so I will start now with my research. So we were thinking, how can we solve this problem of the training data, like searching for other options. And since our background, me and my collaborators, we are basically civil engineers with a background of earthquake engineering, and we were aware of this information that we usually use. I think you are familiar with fragility curves. Fragility curves are these functions that associates the intensity of the demand a building experienced during the earthquake, in this case, or disaster, and the probability that this building will reach or exceed certain level of damage. Okay, so for decades or more than decades, many researchers have been creating these fragility functions empirically or analytically. Okay, so we proposed in one of our first studies is to neglect collection of training data and use fragility functions as a new constraint to calibrate a machine learning algorithms. So this is, you can see in the bottom of this slide, if you want to know more details of this idea. This was our first idea of replacing training data with fragility curves, and we achieve a high accuracy in the same level of the traditional machine learning algorithms. But it has some limitations. I must confess that it works on a specific bidimensional space, and the way we calibrate was just exhaustive search. It wasn't very elegant. So this slide shows actually a bit more detail of the results of our first algorithms. We achieved between 80 and 85% of accuracy. As I mentioned, it's in the same level of traditional methods. And in our second stage, we want to improve our algorithms, the way we calibrate these functions. So we actually adapt a very popular machine learning algorithm that is logistic regressions, in which we include information of the fragility curves. And doing this, we were able to have a more versatile or robust calibrate discriminant functions. And now it uses optimization techniques to calibrate the parameters, and it was not restricted only to bidimensional space. It was, and we can work with n-dimensional space. And if you want to know more details of this work, you can see in the bottom of this slide the title of our published paper. Okay, so again, this is a bit more of details of our results, in which we use these methods to identify the damage and collapsed buildings during the 2011 Tohoku earthquake, and we achieved 87% accuracy. So we were happy because of our second paper. Our methods were very useful, but when we show these results of these methods to other communities, to our colleagues, they emphasize that it works, but it's limited only to disaster in which we have fragility curves. Fragility curves was our constraint, right? If we go to some areas, some countries that doesn't have fragility curves, or any other kind of disaster in which we don't use fragility curves, we cannot apply the method, okay? But we noticed that there are in some cases, we have information of the disaster intensity, the demand. Although we don't have fragility curves, at least we can have this information. So we decided to work on this constraint. Let's assume that a disaster happened. We can have an estimation of the demand, but we don't have fragility curves. Like, for example, I'm showing on the left side an estimation of the tsunami inundation depth during the 2011 tsunami earthquake in Japan. And we propose a different approach in which we have this hypothesis. In the areas in which the demand is very low, like the green polygon in the figure, we can assume that these areas contain samples of non-affected buildings. Most of them are non-affected, okay? Perhaps there are some outliers. And in the areas in which the demand is medium or high, we will assume that we have these two different class of buildings. I mean, collapsed building and non-collapsed building. Starting from that, we propose an algorithm that can calibrate it automatically without collecting training sample as a standard fashion. And if you want to see again the details of this work, you can read our paper. The name of the paper is in the bottom part. So I just want to show here some examples of our last method. So this is actually not an earthquake, but this is a flood due to heavy rainfall. We developed these algorithms in a general way that it can work not only on earthquake and tsunami, it works on any kind of disaster. So this is just a case of a flood map. Here I'm showing another example due to the landslide of the Hokkaido earthquake in 2018. I think it was also in 2018, in which we collect samples automatically, again, using the intensity. See, you see in Japan there's a very large strong motion networks, and we were able to identify which areas, which mountains areas has a very low PGV, peak ground velocity, and we extract some features, and you can see here the features we extract from the radar images is here, the subdimensional space, and we also identify the areas in which the PGV was very high, and we collect the same features, and you can see here. So you can see here that although it seems similar, there are many more samples in the top area of this bidimensional space that is actually samples of that we collect on the landslide. So this is just a close-up that you can see that the algorithm actually uses the low PGV areas to collect, to create a function that englobes only this area, and all these outliers we classified as landslide. And I think you can see here we identify some of the landslide. You can see on the right side the white dots are the landslide we detect, and perhaps you notice that the algorithm didn't identify all the landslide. This is because the radar images usually takes images from one side. In the product we use, the satellite was on the left side, so we are only identifying landslides that occur on the left side of this figure. Okay, if we want to identify all the landslide, we have to use another pair of products in which the radar take images from the right side, from the other side. Okay, it is not because of the limitation of the method. It's just basically the nature of the images. So I think that's all. So as a conclusion, I would say that it is possible to calibrate the machine learning algorithms automatically without collecting training data in the standard fashion. And this is very important, very useful for disaster relief or early disaster response.